Assalamualaikum. My name is Muhammad Masafi from Group G. Today, we'll be presenting a science review of the internal combustion engine, or ICE or ICE. In this presentation, we'll be covering 6 points. The first is introduction, the second is schematic drawing, the third is method analysis, the fourth is performance calculation, the fifth is improvements, and finally references. Group G consists of Muhammad Izzat Hanif, Noor Atirah Fatihah, Amirul Asmawi, Muhammad Atif Ajwad, and myself. I'll start with the introduction. The ice was first developed by Christian Huygens, a Dutch physicist in the year 1673, where he uses gunpowder as fuel but quickly learned it was impractical. Next, we'll see what principles the ice follows. The basic principles are split into 3 cycles. We have the Carnot cycle, the Otto cycle, and the Diesel cycle. The Carnot cycle can be said as the most efficient cycle that can be executed in between heat source and sink temperatures. Based on this pressure volume diagram, we can see that the temperature between state 1 and 2 and the temperature between state 3 and 4 are constant. We can clearly see this a lot more clearer on this cycle's temperature entropy diagram. This slide shows a better visual representation of what is happening in between each individual state. The Otto cycle paints a different picture for its pressure volume and temperature entropy diagram when compared to Carnot cycle. This cycle works by compressing the air and adding heat to it, expanding the displacement volume and rejecting that heat. This is pretty much works in the opposite way of how Carnot cycle functions. The Diesel cycle shares a lot of similarities to the Otto cycle, but still has its differences too. The main difference happens in between state 2 and 3, where heat is added to the air. This is called pressure constant heat addition. The key challenges for ICE are to lessen climate change due to ICE emissions, to integrate new fuels in ICE, to lower health effects due to ICE noxious pollutants, and to cut down consumption of primary energy sources.
For the internal combustion engine, we have two types of engine. The first one is spark ignition, and second one is the compression ignition. We have two and four stroke engine for these two types of engine. For the engine terminology, we have two valves, intake and exhaust, displacement volume, VD, cylinder, the inside one is the piston. We have BDC, a stroke, and TDC. This one is a carrier volume. For two-stroke cycle engine, we have compression stroke and power stroke. This one is the actual PV diagram for the two-stroke engine. This is an ideal PV diagram for two-stroke engine. For two-stroke engine process, compression stroke begins with fuel and air mixture going into the engine. The ignition begins, and the piston will go down to the BDC, and the exhaust gas exit from the engine. For four-stroke cycle engine, we have intake stroke, compression stroke, power stroke, and exhaust stroke. For this four-stroke engine process of compression stroke, power stroke, exhaust stroke, and intake stroke. Step 1 in compression stroke move to the step 2. In power stroke, step 3 move to step 4. In exhaust stroke, step 1 move to step 5. And intake stroke, step 5 move back to step 1. So for the petrol engine schematic diagram, we have a spark plug for the ignitor. This is the inlet and the outlet for the exhaust. This is the crankshaft, PDC and TDC. For the diesel engine schematic diagram, we have same as the petrol engine schematic diagram, but this time we use fuel injector. For the PV diagram of the four-stroke engine, a little bit different from the two-stroke engine. We have a 5-state. This is ideal, and this is an actual PV diagram. Starting from step 1, step 2, step 3, step 4, and step.
Assalamualaikum and hi, my name is Muhammad Izzat Hanif. Now I will talking about method and performance. Method and performance is divided to two parts, which is data and equation. This is the data collected during the experiment. Now the explanation. The baseline show the well-known result that combustion ignition engine are substantially more energy efficient than spark ignition engine. Specifically, the DSI and the DCI have 10% and 20% less consumption respectively than the BSI. The extra 1-2% efficiency is described to be better ability of mixing the natural gas fuel with air, which improve the cold start combustion. The energy consumption of the CNG hybrid is according to this table, slightly more economic than the DCI hybrid. a result that is not in accordance with the alternative estimate, which placed the hybrid and gasoline hybrid on a par. The differences in the study CNG considered the situation in 2020 where the ICE hybridization is used a dedicated design as the last column of the table. Hybridization are particularly favorable for CNG PSI energy consumption because electric assistance allow performance criteria to be met a 20% reduction in the displacement of the ICE as compared to 2002 base, thereby delivering the full benefit of CNG higher octane rating and associated higher compression ratio. The DSI engine has lower fuel consumption than the PSI because it's run in lane burn mode. For DSI configuration, the following assumption we made: J below 50 Celsius, the engine operates in homogeneous mode. At stoichiometric condition, not lane burn. J above 50 Celsius in a range of a low speed, low to mid load, the engine is under lean stratified condition with the typically lower fuel consumption of the I engine. Now I will talking about the equation. The equation is when used is thermal efficiency, fuel efficiency, and engine displacement.
When discussing about an ICE or internal combustion engines, there are many calculations that can be made regarding this topic. Here are some of the calculations including power output, torque, fuel efficiency, thermal efficiency, and engine displacement. Here are some explanation about those calculations, which is power output measures how much work the engine can do in a given amount of time. Torque is the engine twisting power, which is crucial for tasks like accelerating vehicles or turning machinery. Fuel efficiency shows how far the engine can go on a contained amount of fuel, indicating how efficiently it uses fuel. Thermal efficiency measures how well the engine turns fuel into useful work without wasting energy as heat. Engine displacement serves as a critical metric in understanding an engine size, power potential, and performance characteristics. Generally, engines with larger displacement have greater capacity to process air and fuel, resulting in higher power output. As such, engine displacement is often used as a standard measure for comparing and classifying different engines and vehicles.
After analyzing the data, it appears that implementing of internal combustion engines could lead to improve in control the pressure rise in the cylinder, expand the amount of gas line that a cylinder can be accessed without preventing noise, and increase air pollutants. This appears to be challenging issue to solve right now. It's possible that creating alternative fuel with a similar overall energy content but a slower rate of heat release at the high temperature will be necessary to find for the solution. Besides that also, the control the ignition timing, particularly with a view of control speed and load transits. A related but distant subject is the growth of extremely diesel engine which permit low temperature combustion, allowing for the more control over transits and ignition timing as well as the creations of greater specific power that's the HCCI method. At the price of the less favorable reduction in the emission level, the necessary of the fuel injection equipment of the high injection pressure and the capacity of the sealant of the leaf and speed of the nozzle leaf injection rates, shaping are very essential in the content of the both of this paragraph and this subsection. Besides there also, there are the advanced concept. Firstly, improvement of the low speed response. The obvious goal is the boost of turbocharger low speed reaction. Less focus is speed of overcoming the mechanical or rotor inertia electricity and mechanism for assistance for the fluids. Besides that also, there are electric turbo compoundings is another way to harmless with heat. The idea has a potential to boost power density while also improving fuel economy and producing a target efficiency engine with a turbo compounding.